Welcome to the debate. Today our discussion centers on a 3I Atlas. It's the third confirmed interstellar visitor to our solar system. And this thing is, well, it's staggering, quite unique among its peers. It's characterized by its immense size. We're estimating between 5 and 11 kilometers across, and some truly bizarre physical activity. We're talking glowing nickel vapor and gas jets shooting straight toward the sun. The sheer novelty of this object, it really forces a critical scientific question. Does this unique combination of mass, activity, and composition we're seeing in 3I Atlas, does it represent a black swan event? Something that means we have to fundamentally revise our current models for how interstellar objects form their chemistry? Or does it maybe just confirm the expected spectacular, but expected diversity within this known population of galactic castaways? So I'll be arguing that 3I Atlas presents a suite of data points that fundamentally challenges our existing theoretical frameworks. It really demands a critical revision of our models of this, well, extrasolar material.
And I'll be taking the position that while 3I Atlas is, yes, undeniably a spectacular discovery, it certainly pushes the observational limits of what we can detect. Its properties ultimately confirm the expected statistical range and diversity of interstellar objects. It's an extreme data point, sure, but I think it fits within the context of robust galactic material exchange models. Models that maybe just require some refining that outright rejection.
See, I think 3I Atlas is an anomaly that we can't just, categorize away as a statistical outlier. We really have to consider the complete set of observations. When you compare it to its predecessors, Oumuamua and Borisov, this object is fundamentally different. It demands a radical reevaluation of what we expect from extrasolar material. Let's start with the scale. Its mass is orders of magnitude greater. We're talking maybe 1,000 to perhaps 100,000 times heavier than one Oumuamua. I mean, if Oumuamua was a pebble, Atlas is a mountain. It's the undisputed heavyweight champ we've detected so far. An extreme outlier like that suggests that our initial statistical understanding, which was built on just two much smaller objects, was severely incomplete, especially regarding the upper limits of size and mass within the entire population of ejected materials. You just can't easily dismiss a factor of 100,000 as mere noise. And beyond the size, it's the chemistry that truly sets it apart, I think. The detection of glowing nickel vapor. That's a direct spectroscopic look at what some scientists are calling alien chemistry. Now, nickel is a metal forged in stars, right? And finding it in a volatile state here, well, it fundamentally alters our assumptions about extrasolar ices in planetary building blocks. And finally, the dynamics are just counterintuitive. These giant jets of gas shooting straight at the sun. That's highly unexpected. It suggests a unique internal structure, or maybe a composition unlike any local comets we know. This collection of unprecedented characteristics, taken together, I believe it moves beyond just a statistical curiosity. It really enters a realm of a truly unpredictable, high-impact black swan event.
Okay, I appreciate the powerful framing there. But the discovery of 3 Atlas, while certainly spectacular and, requiring intense focus from the astronomical community, I think it's best understood as providing the necessary empirical confirmation of how diverse the universe actually is, rather than suggesting our core physics or our formation models are somehow broken. I mean, look, we only have 3 data points so far, right? Oumuamua, tiny, really enigmatic. Borisov, a modest, older comet. And now Atlas, this massive, younger comet. The huge range we're observing is, well, it's exactly what a high-volume galactic swapping mechanism operating across billions of star systems with all sorts of varied gravitational environments would predict. We should expect a wide range. The object's extreme size, 5 to 11 kilometers, is likely just the upper, rarer end of the expected size distribution.
Our models have always accounted for a power law distribution of ejected bodies. Now we actually have proof of that high mass tail. It is massive, yes, absolutely. But its hyperbolic trajectory, defined by an eccentricity over 6, that simply confirms its extrasolar origin. It's got an eccentricity far outside anything but our sun, which is exactly what we were looking for in an interstellar visitor. And what's more, the object acts like a comet. It shows activity, it forms a coma and a tail, and it's redder than our local rocks. This all confirms its exotic origin. The activity observed as far out as that's roughly 600 million billion kilometers from the sun, nearly Jupiter's orbit, and way beyond the water ice line, that simply suggests we're dealing with tough, rugged material, and this reinforces the idea that diverse building blocks exist across the galaxy, which, is already a core concept in stellar formation models.
You're trying to normalize the scale by just placing it on a statistical curve. But I think the issue is the inherent assumptions built into that curve, particularly regarding ejection efficiency. This object seems to defy those assumptions. Let's focus squarely on the scale again. 5 to 11 kilometers. We're talking about a major planetesimal nucleus being ejected here. Now, current ejection models, which typically rely on gravitational interactions, things like planetary migration or slingshots in young dynamic systems, they tend to favor ejecting smaller objects much more frequently. Ejecting something this large requires a massive gravitational kick, maybe a close encounter with a Jupiter-sized planet, or perhaps even a binary star system interaction. And when you couple that with its relatively young age, around 0.8 billion years, compared to Barrostro's estimated 1.7 billion years, it suggests a highly efficient, maybe even violent, ejection mechanism from its parent star system.
And one that occurred relatively recently. Cosmically speaking, if objects this massive, this pristine, and this recently formed are, routinely being flung into interstellar space, then our estimates of interstellar material density and mass transport across the galaxy, they must be dramatically increased. We're not just confirming a tail, we might be the shape of the entire distribution function and the underlying physics that create.
That's a compelling point about the kinetic energy needed for ejection, I grant you. But I would argue that the models are actually flexible enough to accommodate this. The source material itself suggests we might expect, maybe one interstellar object crossing the inner solar system. If there are literally trillions of these objects wandering the galaxy, finding one up to 11 kilometers across is, statistically inevitable, given enough observational time. And while current models might, yes, favor smaller ejections, they certainly don't exclude the possibility of massive ones. We only observe the results of those rare, massive gravitational perturbations. We haven't actually detected an ejection event itself. We've only found the artifact later.
So instead of seeing the size as a breakdown of the models, maybe we should view it as confirming the existence of extreme events physics, a tail to the distribution that we simply hadn't mapped yet because our sample size was, frankly, tiny. This object forces us to prioritize searching for those high-mass ejections. Sure, but it doesn't necessarily mean throwing out the fundamental physics of gravitational scattering.
I'm still not convinced that the statistical tail argument can really account for the specific material properties we found. The chemistry, that's real departure, I think. Nickel vapor, detected for the first time in interstellar comet. It offers a clear spectroscopic fingerprint of truly, alien chemistry. Why is it so significant? Well, nickel is an element that needs very high temperatures. We're talking thousands of degrees Kelvin to form and condense. In a typical protoplanetary disk, nickel would be locked away deep inside highly refractory, non-volatile rock material, condensing close to the parent star. So for us to see it vaporizing way out at far beyond the typical sublimation point for common ices and even most metals, it means one of two things. Both are pre-evolution.
Either this object formed in an entirely different, perhaps much hotter environment where nickel could somehow be incorporated into a matrix that's easily sublimated later, or its parent disk underwent radial mixing processes far more vigorous than what we think happened in our own system, carrying that volatile metal component way out before it got locked into the. This strongly indicates radically different stellar or environmental conditions during its formation. And that's a critical data point that forces theoretical revision of disk chemistry, not just a refinement of composition.
Okay, I come at this from a slightly different perspective. While the observation of glowing nickel vapor is a significant first, absolutely, the element nickel itself is, it's entirely known and common, right? It's a universal product of stellar nucleosynthesis. Its detection here, I think, speaks primarily to the spectacular advancement of our current observational capabilities. The precision we get from ground-based telescopes like the Ground Telescope Canarias, it lets us snag spectra we simply couldn't have dreamed of getting from something like Oumuamua. The material isn't physics-defying, it's just presenting itself in a novel way. We're observing a volatile metal that's somehow incorporated into an icy matrix. Now, while it does force us to refine our understanding of how these elements get locked into extrasolar cometary matrices, it fits squarely within the current framework of galactic elemental distribution. It tells us that comets from other systems might have more rugged structures or maybe different mixtures of carbon-based ice that can hold on to these metals until they get much closer to a star. So yes, it's a crucial update to our composition models, certainly, but it's an update based on new empirical data points fitting into an established chemical framework.
All right, chemistry aside for a moment, let's address the peculiar dynamics of the coma. Those giant jets of gas
gas shooting straight toward the sun. That poses a distinct dynamical problem. It really seems to challenge established sublimation models. I mean, in our local comets, traditional sublimation predicts jet activity directed away from the sun, mainly due to the pressure of solar radiation, or maybe along the axis of rotation if the object is homogeneous. These solar-facing jets observed in Atlas strongly suggest, well, either an extremely unusual distribution of highly volatile materials deep within the nucleus that are venting unexpectedly, or maybe a peculiar non-uniform internal heat transfer mechanism, something that's somehow allowing pressure pockets to build and release gas predominantly on the sunward side. This implies an asymmetry or an internal complexity, perhaps voids, fractures, layers of different composition that our current sort of simple baseline models for cometary structure are just missing when we apply them to massive extrasolar bodies. This directly impacts how we model things like rotation and structural integrity for these objects.
That's a compelling argument, but have you considered the geometric factors that might be at play? Sublimation is a really complex process, you know. It's highly dependent on the comet's rotation rate, its specific surface topology, the angle of the solar flux hitting it. We know the activity started way out at 4, which confirms we're dealing with high refractory, tough material that's already difficult to sublimate. So the observed solar-facing jets, they might simply be the result of a geometric effect coupled with rotation. If the comet has a non-principal axis rotation, a tumble, or if it presents a highly fractured surface, which seems likely for a massive ancient object that's traveled interstellar space, localized sublimation might occur from a specific fissure that just happens to be facing the sun at a certain angle during its rotation, making the observed jet appear solar-facing from our perspective here on Earth. I think we need far more high-resolution data on its rotation and surface features before we conclude that an entirely new physics phenomenon is required. This calls for refinement in our models of sublimation and surface dynamics, especially for these hardier, extrasolar ices, focusing on geometric complexity, not necessarily a wholesale change in theories of interstellar origin.
Okay, let's bring this back to the black swan designation for a moment and the operational reality it created. The classification as a unique, unpredictable event seems validated, I think, by the operational response of the International Asteroid Warning Network, IAWN. IAWN, which is this international group focused on coordinating and tracking potentially hazardous objects, they were in a dedicated Comet campaign, specifically focused on refining tracking technology for this hyperbolic mover. That mobilization is critical evidence that 3 Atlas isn't just some statistical curiosity. It offered a critical, high-speed test case for planetary defense against objects whose arrival trajectory is inherently unpredictable because they originate outside our solar system's plane, and whose potential impact severity is high given that 11-kilometer maximum size estimate. The IAWN campaign, to me, underscores its unique significance as an unexpected, complex potential threat that really stresses our current tracking infrastructure.
I'm sorry, but I just don't buy that the operational response validates the scientific classification of black swan. IAWN's mandate is basically to track anything that moves fast and comes near Earth, regardless of its origin. This campaign is a vital, yes, absolutely necessary dress rehearsal for tracking any fast near-Earth rock, whether it's interstellar or just something flung in from our own Oort cloud. And crucially, the black swan theory applies to phenomena that are supposed to be fundamentally unpredictable, outside the realm of expectation. But the source material itself confirms we expect interstellar objects, maybe even as often as one a year. Atlas simply confirms the statistical existence of the large end of that expected population. The scientific value isn't in its supposed unpredictability, but in the specific data we gathered, the orbit, the composition. That data helps build the essential statistical foundation for the expected population of interstellar objects. It confirms that space is connected, stars swap materials. It proves that the range of the population is wide, not that the universe is somehow radically unpredictable.
I think we've established that 3I Atlas presents a compelling suite of unique characteristics. Its unprecedented size suggesting really vigorous ejection physics, the exotic nickel chemistry demanding a rethinking of extrasolar formation temperatures, and those unexpected jet dynamics pointing to complex internal structure. Whether we ultimately agree on the label black swan or simply call it the extreme edge of the distribution, the sheer volume and the novelty of the data gathered from the single object, it necessitates a critical re-examination of our theoretical models, especially regarding extrasolar composition and the specific processes that eject such massive bodies from their parent systems. I maintain the existing frameworks are insufficient to explain the combination of these factors without substantial modification.
While 3 Idalis is undoubtedly the boldest interstellar tale yet, I see its properties as fundamentally serving to illuminate the true vast diversity of the galactic castaway population. The observed differences between Borisov and now Atlas in mass, activity, composition, they reveal the immense range of thermal and chemical conditions across different star-forming regions in the galaxy. Atlas provides that essential empirical anchor point for the high-mass tail of the distribution. It forces us to refine and strengthen our existing theoretical frameworks of the stellar material exchange to better account for these observed extremes rather than, abandoning them altogether.
Right. Regardless of whether we land on calling this a model revision or a model refinement event, I think we both absolutely agree that 3I Atlas is a crucial frozen time capsule, one that's now thawing right before our eyes. It definitely promises more insight as ground teams and even probes like Mars Express continue to observe its perihelion pass coming up on October 29th. The material offers substantial complexities, everything from its internal integrity to its chemical origins, that clearly require continued rigorous multi-perspective examination to fully understand our place in this galactic neighborhood.